Welcome back, everybody. So today we're going to look at some questions related to section 4.4, which was on the fundamental theorem of calculus. So that was part 1 and part 2. So there are kind of two parts to it. And this is the fundamental theorem of calculus. So this is a really important section. This is the section that really defines how we operate with integrals in single variables. As well as working with integrals as functions. So I know it says section 5.3 here, but that's from a different textbook. This is for section 4.4 for us. So let's just note that what the fundamental theorem of calculus is. So there's two parts to it. So for us, we defined part 1 as the way that we evaluate definite integrals in general. So if we have the integral from a to b of little f dx, that is equal to capital F of b minus capital F of a. So note our assumption is always that f is continuous on our interval ab. So we'll note that that's our main assumption for our theorem. And so what this is telling us is that we can compute the integral by using antiderivatives. So we'll just note that capital F prime of x is equal to little f of x, meaning these are antiderivatives. And again, this is just telling us the area under the curve of a function. So the area under the curve of a function is related to the difference in its antiderivatives at values. So that's our first main connection. And then part 2, which is also incredibly important because it allows us to define functions as integrals. So now my function is representing all of the possible areas. So at any given point x, that's going to give me the areas. And because this is a continuous distribution of areas, so as x moves, there's an infinite number of areas that it's representing, all of which will be corresponding to each other, where any x value corresponds to one particular area value. This describes a function itself. And again, f is continuous on AB. Then g of x is equal to this integral, and g is differentiable. So we get differentiability and continuity for this area function. So then g prime of x is equal to f of x. And this means that then if we describe this area function, we can describe its increasing and decreasing behavior. We could keep going and find concavity values, and then describe points of inflection as well. And I'll just note in general, if we have something a little bit more complicated than just x, right? Because note the derivative of x is just 1. So if I've got something, more complicated that has some derivative u prime, then when we take the derivative of g, what we're going to get is still f prime evaluated at our variable limit times u prime of x. So note the chain rule still applies to this new type of function. So we're still using the chain rule in general. So for these examples that we're going to start with, these are going to be more AP FRQ style questions where we're using graphs and tables to calculate. So note, some of these will say no calculator, some of these will say calculator, so you'll be able to use your calculator for some of these. So let's go ahead and get started here. We've got this graph f on the right, and we're going to let g be the integral from 0 to x. So we're integrating from 0 to x, They don't put it on here, but we'll assume that we're going to 7, right? So we don't know any information other than between 0 and 7. So let's go ahead and get started. So g of 0 is the integral from 0 to 0 of f of t dt, which is just 0. That's one of our properties of integrals. So then g of 1 is going to be the integral from 0 to 1, which is the area underneath the curve here. That's clearly a 1 by 2 rectangle, so the answer will be 2 for the area. And then we can keep going. So g of 2, if we do the area from 0 to 2, we've got 2 2x1s, so that's 2, and then half of that in that rectangle is going to be 5. G of 3, we'll take that 5 and add, looks like 2 more. So we'll have 7. And then g of 6, if we go over to 6, we're going to get this trapezoid, which we can split, though, into a triangle and a rectangle. So we'll get -2 here, and then that's a 2 by 2, so that's going to be -2 as well. Yes, so the area underneath here is -4, so that means we go back to 3 on our graph of g. So keep in mind, below the x-axis is negative, above the x-axis is positive. So we've got those values, and those are going to be useful to us a little bit later on. So let's move to the second part. On what intervals is g increasing? So we need to know, what is the derivative of g? Well, from here we can see we've got this basic 0 to x integral, so that's just going to be f of x. And we can see that f of x is greater than 0 on the interval, open interval, 0 to 3, right? So everywhere here, f is positive above the axis. Thus, f is, g is increasing on 0, 3. And again, we're including our explanation with some evidence, right? So we're saying g is increasing, and our evidence is that the derivative is positive there. All right, so where does g have a maximum value? So note, there's no prefix to that maximum, so this is going to be an absolute maximum, which means it can either occur at the endpoints or relative max values. So we need to find if there's any relative maximums, and we need to check the endpoints. So we'll just note g of 0 we already know is 0. G of 7 we can quickly calculate. So we know g of 6 is 3. So all the way up to here, this is going to be 3. So then if we add on this additional -1, it looks like, then g of 7 is just going to be 2. So g of 7 is equal to 2 by our geometric calculations. So now we need to find where g prime of x equals 0, which is pretty easy to see that that occurs at x equals 3. And note it has to be within the subinterval, can't be at the endpoints or it's kind of redundant. So at x equals 3, and f prime changes from positive to negative at x equals 3. Thus, there is a relative max at x equals 3. So we need to check x equals 3. If it was a minimum, we wouldn't have to check it. We could just conclude that g of 7 was our maximum. But now we need to compute g of 3, which we already have above. So by part A, we know g of 3 is 7. So g of 3 equals 7 is the absolute max, is the maximum value. And the maximum value is simply 7, but you can say g of 3 equals 7 as well. All right, it says evaluate g prime of 2. So that's pretty easy. That's just going to be f of 2. So if we look on our graph, f of 2 is 4. Now, something that might also be asked for is maybe like g double prime of 2, which would equal f prime of 2. And if you look at f prime of 2, there's a cusp. So the second derivative does not exist, which means that that value would be a possible inflection point, right? So we'll do that in the next part here. So part E, so g double prime of x equals f prime of x equals 0 or does not exist at x equals 1, 2, and 3. So if we look at our graph here, we've got, sharp turns at those points, up 5 and 6 as well, but if we look at 5 and 6, it's actually flat all the way through. So we've got 0 slopes from 5 to 6. So, and on 5 to 6, but our inflection point has to be at a point, right? So we don't need to actually worry about 5 to 6 then. So because it's a completely constant function. We also don't need to worry about 0 to 1. So no, we could cross out the 1 value. That one's not going to count either. But we'll note we just need to show where it's changing sign. So f double prime, so g double prime changes sign only at x equals 2, so it changes from positive to negative concavity. So concave up to concave down. At 3, it goes from concave down to concave down. Thus, x equals 2. Thus, 2 comma, what was g of 2? G of 2 was 5. 2, 5 is a point of inflection. All right, so this is kind of a standard example. You start with your integral function, do some integral calculations, then we start taking derivatives and doing some derivative work with maxima, minima, and points of inflection. All right, so then looking at number 2, now we're going to be using some Riemann sums and doing some calculations here. So we're given that water is draining out at a variable rate. So R of t, let's note, is the rate, not the quantity of the water. It's the rate at which the water is leaking out. So it's the absolute value of the rate, though, so we're not going to use negative or positive numbers, obviously. Everything will just be counted as positive. So our first step is to approximate the amount that has leaked from the tank from 0 to 35 minutes using a Riemann sum with right-hand endpoints and 5 unequal intervals indicated by our chart. So that means from 0 to 35, we're going to have 5 uneven intervals, which are given. So our first subinterval is 0 to 5, second subinterval is 5 to 10, third subinterval is 10 to 20, then 20 to 30, and then finally 30 to 35, which we can just mark off on our graph here. So we've got 0, 5, 10, 20, 30, and 35. So we're going to use right-hand endpoints. So we'll start on the right, and we'll leave off the last endpoint because we can construct our rectangles here. Now this is a calculator problem, so you can use your calculators. So then the volume using right endpoints is approximately, so our delta x is changing each time, so keep that in mind. So we're going to do each rectangle as a separate calculation. So the first rectangle is 5 times 5. The second rectangle is 5 times 20. The third rectangle is 10 times 30. The fourth rectangle is 20 to 30, yeah, 10 times 15. And then the last one's just 0 because it has no height at the right endpoint. So let's go ahead and calculate. So that's going to be 25 plus 100 plus 300 plus 150. So we'll get 575 gallons. So approximately 575 gallons have leaked out of the drain, or out of the tank. Okay, so that's pretty simple. And then for B, we're going to now do a calculation with this integral expression where we're dividing. And this one is going to be from 4.4, and this is average value. So no, average value is 1 over b minus a integral a to b of f of x dx. And it's the average value of the f function. So we're going to be finding the average value of r on our interval. Now, it doesn't tell us how to calculate it, and we don't have the actual function, so we're still going to have to use Riemann sums. So for this part B, for this example, since it doesn't tell us, we're just going to come up with some method for doing it. So if I look at the points where we are located, so we're between 10 and 30, and we want, some nice values, I think I'm just going to use trapezoids. So I'm going to do trapezoids with 2 subintervals, just because those occur at nice points. So we're going to construct some trapezoids here. And actually, I think, because those are linear pieces, I think we can get the exact area. We can get the exact area, because those are just linear. So let's see. We can do this as, probably 2 trapezoids is going to be the best idea. All right, so let's go ahead and calculate that down here. So we'll do the integral from 10 to 30, r of t dt is equal to, so our first trapezoid, let's do some calculations here. So that's, 20, 30, that's 10, and then that's 15, and that's also 10. So we'll have, that's going to be 1/2 of 10 times 50 plus 1/2 of 10 times 45. All right, so we'll put that calculation in here. Note, for calculator questions, you don't actually have to write out the work necessarily. You just need to put the correct answer next to your integral. But let's see, 5 times 45. So that's 475. Okay. So then one over 20 integral 10 to 30 r of t dt is equal to 475 divided by 20, which is 23.75 gallons per minute. So the average rate at which water is leaking out of the tank from t equals 10 to t equals 30 is 23.75 gallons per minute. So the key here is the explanation. So we've got the value, now we just need to put the value in context. So the average rate at which we are leaking is the value on the time domain, and then using that value appropriately. So the average rate at which water is leaking. Sorry, at which water is leaking out of the tank from t equals 10 to t equals 30 is 23.75 gallons per minute. And we can see, looking at our values from 10 to 30, that seems reasonable. All right, so then for part C, it asks us to calculate R prime of 25. Now, again, we don't know what R is, so the only thing we can do is reference our table. So if we're finding R prime of 25, we're going to find the two closest points to 25. In this case, it's going to be 30 and 20 for t. And then we're going to do the secant line, or the difference quotient calculation between those 2 points. So that is that R prime of 25 is approximately R of 30 minus R of 25 all over, 20. So R of 30 is 15 and R of 20 is 30 all over 10. So that's going to be negative 15 over 10, or negative 1.5 gallons per minute squared. So note, our units on the top are gallons per minute, and then our units on the bottom are minutes. So it's gallons per minute, or gallons per minute squared. So now it says interpret the meaning of that value. So this means that the rate at which water is leaking out at t equals 25 is decreasing by 1.5 gallons per minute. So note, this is the rate of the rate. So we can say that the rate is decreasing. You could also say the rate of the rate at which water is leaking is negative 1.5 gallons per minute. So the rate is decreasing, and again, at that specific moment in time. And then for part D, this is going to be a graphing calculator question. So this is if we model the rate at which the leak is occurring with this Q function, at what time is the water leaking fastest on the interval 0 to 35? So we want to know at what time is the water leaking fastest. So what we would want to do here then is set Q prime of t equal to 0, and then look for where we have a sign change from positive to negative. So I'll let you put that into Desmos if you want to, since we haven't discussed the graphing calculator too much, but it's a pretty simple calculation. Let's see. Okay. And we're on the interval 0 to 35, so you want that to be your x interval. So we can calculate when the derivative is at its maximum. So it looks like when t is 18.805309, so 18.805. And Q prime t changes from positive to negative at t equals 18.805. And that is minutes. So again, you could check that by taking the derivative and graphing it. But note, for calculator questions, you can do all of the work on your calculator and then just provide your explanation. You don't explicitly have to find q prime of t, although it can be helpful. All right. So let's go ahead. The next question actually is a question that I discussed in a previous video. So this question was either in the 4.4 notes video or the 4.5 notes video. I don't remember which. So you can look at that one there. So we've got problem number 4, problem number 5, and problem number 6. So I think I'll pause here. We can take a break here and I'll post a second video with these remaining solutions. So if you do have questions on any of those previous answers that we looked at, feel free to shoot me an email or come by the office hours.